Hi all. In this lecture we discuss chapter 5 congruences. Let us begin with the definition of congruence. Given integers a, b and m with m is equal to m is greater than 0, we say that a is congruent to b mod m, and we write a is congruent to b mod m in this manner if m divides the difference a minus b. The number m is called the modulus of the congruence. This definition is already discussed in the undergraduate classes. Equivalent form for the definition, m divides a minus b can be written as m divides a minus b, like this. In particular, a congruent to 0 mod m if and only if m divides a. Hence, A is congruent to B mod M can be written as A minus B congruent to 0 mod M. That is, A minus B congruent to 0 mod M is equivalent to A congruent to B mod M. Both are same. Okay, that is because of this equivalency. A congruent to 0 mod M if and only if M divides A. Okay. Now, if m does not divide a minus b, we write a is not congruent to b mod m. Okay. Now we have a few examples. Set 19 is congruent to 7 mod 12 because 19 minus 7 is 12. Then 12 divides 12. Then we have 19 is congruent to 7 mod 12. 1 is congruent to minus 1 mod 2 because 1 minus of minus 1, that is 2. 2 divides 2 itself. 3 square is 9. 9 is congruent to minus 1 mod 5 because 9 minus minus of 1 equal to 10, that divides 5 divides that number. Okay. If n is even, we know that if and only if 2 divides n. Similarly, n is odd, then 2 does not divide n. Therefore, n is congruent to 1 mod 2, and for even number n is congruent to 0 mod 2. A is congruent to B mod 1 for every A and B because A minus B is 1 divides A minus B for any A comma B belongs to Z integers. If A congruent to B mod M, then A congruent to B mod D when D divides M and D greater than 0. This is because if we have A is congruent to B mod M, that implies M divides A minus B. Okay. But we know that D divides M. Okay. Suppose D divides M. This implies, these two statements together imply that D divides M, that M divides A minus B. That implies D divides A minus B, implies A is congruent to B mod D. Okay. So this is the fifth example. Now we have a number of theorems, all are elementary theorems. You might have seen these theorems in the graduate classes. So, however, we can review all these theorems once again. Theorem 5.1 is congruence is an equivalence relation. So, we have to prove this is reflexive, symmetric, and transitive. For symmetricity, we need to prove that A congruent to A mod M. We know that A minus A is 0. So, M divides 0. This 0 can be written as A minus A. So M divides A minus A for every A. Hence, this A is congruent to A mod M for any positive quantity. Secondly, A congruent to B mod M. That means M divides A minus B. That is the equivalent condition. M divides A minus B. Then we know that M divides B minus A. Okay. A minus B is a multiple of M means B minus A. That is the negative of this number. That is also a multiple of M. So this implies A B congruent to A mod M. So this is also true. So we have symmetry here. Now we have to prove transitivity. Suppose A is congruent to B mod M. That means A minus B is a multiple of M, or M divides A minus B. And from the second congruence, B congruent to C mod M, we have M divides B minus C. So this M divides its sum, obviously. M divides sum of these two. Both are multiples of M, then M divides its sum. Okay, so that sum is nothing but A minus C. So M divides A minus C implies A is congruent to C mod M. So this is theorem 5.1. Now we have theorem 5.2. In 5.2 we have this is the, we can consider this 5.2 is the algebra of congruences. If we have two congruences, A congruent to B mod M and alpha congruent to beta mod M, two congruences with same modulus M, okay, then you have these number of algebraic expressions, or we can write this ax congruent to alpha y, ax plus alpha y congruent to bx plus beta y, and we have a alpha congruent to b beta mod M, a raised to n congruent to b raised to n mod M, f of a congruent to f of b mod M. This is very important. This is true for every polynomial with integer coefficients. ABC are very easy to prove. M divides a minus b and M divides alpha minus beta from the hypothesis. Then M divides the multiple of A minus b again. So that is M divides x times A minus b plus y times alpha minus b beta. That is equal to ax plus alpha y minus bx plus beta y. So this shows that M divides this difference. Then this is congruent to this mod M. This is A part. Then B part we need to prove that the product is okay. So A congruent to M divides A minus B, and we have M divides alpha minus beta again. Then we have A alpha minus B beta, that is equal to alpha times A minus B plus beta times alpha minus beta. Okay, so when you expand this by cancelling the middle term, you can get this one. Okay, so when you expand this, the first term is A alpha, the second term will be B alpha minus B alpha. That can be cancelled with the first term of the second part, B alpha. Then the last term will be B beta. Okay, so you will get this one. Obviously, this is a multiple of M, because A minus B is a multiple of M, and B minus A is a alpha minus beta is a multiple of M. Then we have the sum is also a multiple of M. So we have this is a multiple of M, or M divides this. Hence, you can get B. For C part, we use the B part. If you consider two congruences, two same congruences, A congruent to B mod M, again A congruent to B mod M, then using B you can multiply these two congruences, then you will get A raised to 2 congruent to B raised to 2 mod M. When you multiply the congruence A square congruent to B square with again A congruent to B, you will get A cube congruent to B cube mod M. Then we can continue this, okay, all the way up to this n. So we have A raised to n is congruent to B raised to n. Okay, now we have to prove D part. This is the last one. That is very important. For that we know that A raised to n is congruent to B raised to n mod M for all n equal to 1, 2, 3, etc. If with the assumption that if A is congruent to B with the modulus M. Now you consider a polynomial. Let f be a polynomial. Say f of x equal to a0 plus a1x plus etc plus anx raised to n. Now of course these a's are integers. We are considering polynomial with integer coefficient for the time being, or at least for this chapter. Now we have a congruent to B mod M. We have A square congruent to B square mod M. Consequently, A to A square congruent to A to B square mod M. You can multiply it with any quantity. That is because of this one, ax plus alpha y is congruent to bx plus beta y mod M. So you can multiply it with any x or y, anything you can uh, multiply with this congruence. Then you have a cube congruent to b cube mod M. Correspondingly, we have a3 a cube congruent to a3 b cube mod M, and so on, all the way up to a raised to n congruent to b raised to n mod M implies a raised to n congruent to bn an b raised to n mod M. Okay. Now, from these equations, you can get this a2 times b square minus a square is a multiple of m, or m divides this quantity. From this you can get m divides a3 times b cube minus a cube, etc. M divides an times b raised to n minus a raised to n. We need to prove that f of a is congruent to f of b mod m. In order to prove this, first we evaluate f of b minus f of a. So from this equation, you can evaluate f of b minus f of a. F of b is obtained by replacing this x by b. Then you can get this is a naught plus a1b plus etc. an b raised to n minus f of a is again minus of a naught plus a1 a plus etc. a n a raised to n. Then by taking difference, you will get this first term can be cancelled. The second term will be a1b a1a, that is a1 times b minus a, and we have a2 times b square minus a square, that is the second terms of these two terms, plus etc. an times b raised to n a raised to n. Okay. From these equations, we have a is congruent to b mod m. From this, you can say that this b minus is a multiple of m, and m divides this quantity. That means this is also a multiple of m, and these all quantities are multiples of m. So this m divides f of b minus f of a. Consequently, f of a is congruent to f of b mod m. So if a is congruent to b, then every polynomial satisfies this condition, f of a congruent to f of b mod m. Now we have a couple of examples over here. In the first example, a divisibility test is derived. That is the divisibility test for 9. We can prove that that is same as the divisibility test for 3. In the beginning, the numbers fn equal to 2 power 2 raised to n plus 1 were called Fermat's primes. Later it was found that f5, the fifth number, is not a prime number. It has been proved in the example 2. It has another interesting proof using group theory. Now we have some theorems on these congruences. The first one is cancellation law. If AC is congruent to BC mod M and D is equal to the GCD of M comma C, then A congruent to B mod M by D. That means you can cancel the C with the condition that D should be the GCD of M comma C. Then you can cancel this C so that this congruence changes to the modulus M by D. Okay, this is the theorem. We can easily prove this theorem. Suppose AC congruent to BC mod M, we have difference of these two. AC minus BC, that is A C times A minus B, that is a multiple of this M. Okay, so M divides C times A minus B. Then we know that M by D divides C by D into M minus B, because D is the GCD of both M and C. So this D divides M and D divides C. So you can get M by D divides C by D into A minus B. But we know that since the GCD of M comma C is equal to D, this M by D comma C by D is relatively prime. The maximum, the greatest common factor of this M and C is D. So if we extract that D from M and C, the remaining part will be always relatively prime. So this M by D does not divide the C by D, as it is as its GCD is 1. Then M by D divides this A minus B. So M by D divides A minus B means A is congruent to B mod M by D. So this is what we called cancellation law. Next we have theorem 5.5. In this theorem we assume A congruent to B mod M. If D divides M and D divides A, that means D divides, there exists a divisor for both any two of them, A comma M. Okay, or you can assume B comma M, okay, whatever it may be. So if D divides two of them, you can get the third one is also a multiple of that D. Okay, so if D divides M and D divides A, then you can get D divides this number B. Okay, so for this we assume D is greater than 0, because for the divisibility we need to assume D is greater than 0. If D divides M, then A is congruent to B mod M, implies that A is congruent to B mod D. Okay, that means A minus B is a multiple of M, that is M divides AB, and this D divides M, so D divides AB. So you can get A is congruent to B mod D. That we have already seen the previous part of the chapter 5. So if this holds, you can get D divides A. Then, so if we assume D divides A, and we have A is congruent to 0 mod D. This implies A is congruent to B mod D. And if we assume if D divides A, we have A is congruent to 0 mod D. Okay. By subtracting this, we can get A minus A is congruent to B minus 0 mod D. This implies B is congruent to 0 mod D. Okay. So this is nothing but D divides B. So whenever D divides this A and this M, then you can get D divides this B. This is theorem 5.5. Now we have theorem 5.6. If we assume A congruent to B mod M, then A comma M, GCD of A comma M and GCD of B comma M are same. Okay, so if these two are congruent mod M, then both have the same GCD with this M. Okay, so if for that we assume D is the GCD of A comma M and E is the GCD of B comma M. Then D divides M and D divides A. Okay, from the first statement, D is the GCD of A comma M means D divides A and D divides M. Okay, so we know that D divides B as well. Okay, because our assumption is using the previous part, that means we have D divides A and D divides M, and A is congruent to B mod M. This is the hypothesis, or this is our assumption. So using these two conditions, we can conclude that, along with this you can conclude that D divides this B. Okay, so D divides B means D divides B and D divides M. D already divides M. Then using these two, we can get D divides GCD of B comma M. Okay, so that implies D divides E. So from this you can get D divides, if D is the GCD of A comma M, this D divides E. Okay, now we start with E divides B and E divides M, along with S congruent to B mod M. Then you can get, by previous theorem, E divides A. the third one. Then E divides A and E divides M. Then you have E divides the GCD of A comma M. So that is nothing but D. So the E divides D. So E divides D and D divides E. We will get D is equal to E. This is theorem 5.6. In 5.7, we will prove that A is congruent to B mod M implies A equal to B if mod B minus A is less than M. Okay, because if M divides, for that if M divides A minus B means A minus B a multiple of M. Okay, then this implies mod A minus B is a positive multiple of M. Clearly this M is a positive quantity, so every positive multiple of M is always greater than or equal to M. Okay, every multiple of M is the positive multiple of M starts from M itself, M, 2M, 3M, etc. So if mod M minus B is a multiple of M, then that is a positive multiple of M, then this holds. Then A minus B is a multiple of M or A congruent to B mod M, immediately imply that this M is always less than or equal to mod A minus B. So whenever you got this mod A minus B is strictly less than this M, you can get the only non-negative multiple of M is 0. So this A minus mod A minus B is 0. Consequently, A equal to B. Okay? This is the only possibility. Okay? That means the only possible non-negative multiple of M is 0. That is the idea here. So you can get A equal to B. Now we have 5.8. Assume A congruent to B mod M. If and only if you can get A and B have the same remainder when divided by M. That means if A is congruent to B mod M, then if and only if the remainder when A is divided by M is same as the remainder when B is divided by M. Okay, so for that we use the division algorithm. Since M is a positive quantity, every A you can write A is equal to MQ plus R. This R lies between 0 and M, so 0 less than or equal to R less than M. And B can be written as MQ plus R is a quotient and remainder. This remainder again satisfies the same condition. So we know that remainder, this is 0 and this is M, then the small r and capital R lies in between 0 and M. Okay? Then from these two equations you can write A minus B is equal to R minus R plus M times Q minus Q. So that is a multiple of M. So you can write it as A minus B is congruent to R minus R mod M. Okay, but this R minus R is always less than M. Okay, because of this distance is always less than this distance. So you can get R minus modulus of R minus R is always less than M. So the only possible from this equation you can get A minus B is a multiple of M. That is our assumption. A minus B is a multiple of M, then R minus R is a multiple of M. So mod R minus R is a non-negative multiple of M, which is strictly less than M. So the only possibility is R is equal to R. For the converse part, if you assume R is the small r is equal to this capital R, then by taking the difference you can get A minus B is equal to small m times small q minus capital Q. So that is always a multiple of M. Hence A minus B is a multiple of M. Then A is congruent to B mod M. That is comparatively easy part to prove. Now we have 5.9. This is the last theorem of section 5.1. We can easily prove 5.9 as well. We know that A minus B is a multiple of M means, what is the meaning of this? A minus B is equal to M times some D. Okay, but we know that A minus A is congruent to B mod N. So A minus B is also a multiple of N. That means this implies N divides A minus B. That implies N divides M times D. This implies N divides D, because GCD of N comma M is equal to 1. So N divides this D. So this implies D can be written as, this implies D is a multiple of N. So D can be written as N times D1. From this you can write A minus B is equal to M times D can be written as n times D1. So this implies Mn divides A minus B. So you can get A is congruent to B mod Mn. So these are the elementary theorems in the first part. Now in the next lecture we will move on to residue classes and complete residue system.